Hello friends, welcome to our channel Reds Info Hub. I am Mr. Reddeppa Tanneeru. In this video, we will discuss some of the applications of Biot-Savart's law. In the previous video, we have discussed what is Biot-Savart's law and what is the vector form of Biot-Savart's law and how to find the direction of magnetic field by using which law? Right hand palm rule. Palm rule, right? Yes, in this video we'll discuss about applications of Biot-Savart's law, and especially we have two applications. We'll discuss about two applications. One is how to find the magnetic field due to straight current carrying conductor, and another one is how to find the magnetic field on the axis of a circular current carrying wire by using this Biot-Savart's law. First, let us see finite state current carrying conductor and some of the special cases. So to understand that, let us consider this is a straight current carrying conductor. In this, current I is flowing from bottom to top, and we want to find the magnetic field at a point P which is at a perpendicular distance D from the axis of this straight current carrying conductor. For finding the magnetic field due to this conductor, we already, as we have discussed, we have to divide this into small elements, and we have to find the magnetic field due to such smaller element. Then we have to integrate it to get the total magnetic field, right? So here we have considered a small element dy at a distance y. At a distance y from the center of the line, center of the conductor, and let us say this element. If you want to find the magnetic field due to this element at this point, that is a small amount of field dB, we have to use which law? Biot-Savart's law. According to Biot-Savart's law, the magnetic field due to this small element is given by dB is equal to, in vector form, dB is equal to mu naught by 4 pi into what? I dl sin theta by r square, you can write, or in vector form also you can write I dl sin theta by r square, right? Here in this case, current flowing through the conductor is I and the length of the element is dy. So in place of dl, you have to take dy, and sin theta, sine of the angle between line joining the element and the point and the current. This is the current direction. So if this is 90 degrees and this is theta, then what will be this angle? Total angle is 180. So this will be sine. So this angle will be 90 minus theta. Is it clear? So sine, if you take this angle as a 90 minus theta, you will get sine 90 minus theta is cos theta, and this is y and this is d. For understanding purpose, we have only this part we have redrawn here, and here if you see, this is the perpendicular distance of the point from the current carrying conductor, this is d, and the distance of element from this line is y, and the distance of the point from the element is r. So this forms a right angle triangle. So from this diagram or figure, we can write tan theta, which is equal to tan theta equal to opposite side by adjacent side, that is y by d. Are following? Y by d. From here, just we want actually as a dl, we are taking as a dy, length of the element dy. We want dy. For that purpose, let us write y is equal to d tan theta, d tan theta, and because we want dy, so if you differentiate this with respect to theta, yes, we have to differentiate y with respect to theta. So before that, let us write this by replacing dl with dy. So we'll get dB is equal to mu naught by 4 pi into I into dy to sine of this angle between the line joining the element and point with respect to current. With current is this angle. This is, we can write it as 90 minus theta. So you can write this as a sine 90 minus theta by r square. Further, you can write this as dB is equal to what? dB is equal to mu naught by 4 pi into I into dy to sine 90 minus theta is cos theta. Very good. Cos theta by r square. Now we have to substitute in this case what is dy and what is r and what is cos theta. For that purpose, let us differentiate this. let us take different values for this from the figure. Y is equal to d tan theta. So dy by d theta equal to d into secant square theta, right? Or you can write dy is equal to d into secant square theta d theta. Dy is equal to d into sec square theta d theta, and dy, you got it, right? Then what is r from this diagram? For getting r, you can keep this in one box, right? And for getting r value, let us take what is that, cos theta. Cos theta from this is equal to adjacent side by what? Adjacent side by hypotenuse. So adjacent side is d, hypotenuse is r, is equal to d by r. From this, r is equal to d by cos theta. 1 by cos theta is secant theta. So you can write it as d into sec theta, right? This is r. This is what you have to substitute, dy, then this r. And what about, yeah, cos theta? Let us keep this is cos theta, we'll keep as it is, and we'll try to simplify this relation. Now what you will get is, you can try yourself, just take it out and try substitute this and simplify yourself. Okay, yes, let me do it here. dB is equal to mu naught by 4 pi into I into dy is d into secant square theta d theta is dy into cos theta divided by, what is this, r square. R is d secant theta, r square is d square sec square theta, right? Now if you simplify this further, sec square theta cancel, 1d here, 1d cancel, right? The remaining terms are here I d theta cos theta here, 1d remains here, sec square theta got cancelled, right? Only 1d will remain here. So we can rewrite this as dB is equal to mu naught by 4 pi into I cos theta d theta by d. This is the small amount of magnetic field produced here due to this small element dy. If you want the total field B is equal to, you have integral of dB, you have to integrate dB from where to where, due to this entire conductor we want. So from bottom to top. So by convention, the angle made by this line joining the bottom part with this point will be minus beta, and this angle made by the line joining from the top point to the point top end to the point with this perpendicular line as plus alpha. So we can take this as minus beta to alpha by taking sign convention. That is anti-clockwise angles will be taken as positive and clockwise angles will be negative. So further, it is equal to integral of dB is mu naught by 4 pi into I into cos theta d theta by what, d from minus beta to alpha. Take the constant terms all out, only the variable term is theta, so cos theta term only have to keep inside the integration. So we can write this as mu naught by 4 pi into I by d into integral of cos theta d theta from minus beta to alpha. What is integral of cos theta? That's very good. Sin theta. If we take this in the next step, we can write this as it is equal to mu naught I by 4 pi d into sin what? Sin theta. Then the limits are minus beta to alpha. Minus beta to alpha. Upper limit is alpha, lower limit is minus beta. So while applying the limits, you have to apply for upper limit minus lower limit. So we can write this as sin alpha minus of sin minus beta. So then we'll get this is equal to further mu naught I by 4 pi d into sin of alpha minus of sin minus beta. So this, by using one of the basic properties of trigonometric angles, because sin of minus theta, you can write it as minus sin theta, Here sine of minus beta, you can take it as minus sine beta, so minus minus becomes plus, so therefore we will get the total field B is equal to mu naught I by 4 pi d into sine alpha plus sine beta. This is the magnetic field due to finite straight current carrying conductor. Here I is current flowing through the conductor, D is perpendicular distance from the axis of the conductor to the point, alpha and beta are the angles made with the line joining the top and bottom points with respect to this perpendicular line. Is it clear? Yes. Next we'll see some special cases. So have a note of these points, take a screenshot. Yes. Now let us see some special cases. The first one is if the point lies along the length of the conductor. If the point lies along the length of the conductor, that is, say for example, this is the current carrying conductor, the point is lying somewhere here, then the conductor and the line joining, so that is R bar, position vector. If this is a point, then position vector R bar and DL bar both will be parallel, so theta equal to 0. In that case, if you consider the vector form, dB bar is equal to mu naught by 4 pi into I into DL bar cross R bar by R cube, bar cube cap square, you have to remember that. So these two are parallel means it is DL R sin theta, theta is 0, sin 0 is 0, so we'll get the field due to small element is 0, so due to the entire conductor is also 0 only. So in this case, if the point lies along the length of the conductor, that is theta equal to 0, then what happens to the magnetic field? Total magnetic field B equal to 0. If theta equal to 0, B is equal to 0. That is the first special case and very important case.